Thank you very much, Rachid, for the introduction and the invitation. Unfortunately, I will not be able to speak to you in your beautiful language, because if I do, it will not be a beautiful language. Thank you all for your presence. Rachid asked me to talk to you about the consensus hierarchy, which is a very useful way of classifying objects based on their ability to implement each other. Most of what I have to say in this presentation is based on a very important paper by Maurice Herlihy called Weight-Free Synchronization. And my presentation, if all goes well, will consist of 3 parts. I will start with describing what is this consensus hierarchy, what it tells us about objects. Then I will give you an example of how we determine the level of an object in this hierarchy. And then I will conclude with some comments about what the consensus hierarchy does not tell us about objects to avoid certain possible confusions and misunderstandings. So let's start with the first part. What is this consensus hierarchy? Just to recap the context, we are talking about a distributed system in which a set of processes take steps asynchronously and communicate by accessing shared objects. The objects can fail, but they can only fail by just crashing. They stop taking steps. That's the only wrong thing that they can do. And the shared objects that they use to communicate with one another include, at the very least, registers accessible via atomic write and read operations, and possibly other objects like registers with different kinds of operations like fetch and increment or compare and swap, or other kinds of objects like queues and stacks and things like that. In this context, a key question, a fundamental question is the following. So suppose that your boss goes out and buys a new distributed system. It has n processes. It has some registers. It has some instances of an object B. But what she wants is an object A, different from B. And so she hires you to construct this object A in this system that she bought. And the question is this possible? Can you implement object A using object B and registers? Now, from now on, I will take registers for granted. I will just say, can we implement object A from object B? And I will assume that if I need the registers, they are there. By registers, I mean registers with simple write and read operations. OK, so this is our fundamental question. With object B, can I implement object A? So to give you some examples of this, concrete examples of this question, in a system of 2 processes, can we implement a queue using registers? You know the answer to this question. Rachid told you 2 weeks ago that the answer is no. Or in a system of 5 processes, can we implement a register with a fetch and increment operation using registers with compare and swap operation? Turns out that the answer to this question is yes. So these are the kinds of questions we will be interested in. Again, to remind you, we are interested, by the way, what do I mean when I say to construct an implementation of object A from object B and registers? I mean that for every one of the processes in the system and for every operation of the object A that we want to construct, I must give you an algorithm, a set of instructions, by which the process, the specific process, will execute will carry out the operation. Okay? So, and what does it mean for this for this algorithm to use only object B, it means that this algorithm will only make references to instances of object B and registers. Okay, that's what an implementation is. Now, we are interested in such implementations that are linearizable, which means that although the operations on the implemented object may be executing concurrently, they must preserve the illusion of being atomic or linearizable. And they must also, the implementations must be weight-free, which means that every operation must return its response after a finite number of steps of the process that invoked it. And that should be the case regardless of what the other processes in the system do. Okay, they may be fast, they may be slow, they may have crashed. No matter what they do, this operation should be completed if the process that invoked it takes enough steps. Okay, so again, this is now your task that your boss has asked you to carry out to implement object A using object B. Now, if the answer to this question is yes, it's clear what you have to do. You have to present the algorithm that we talked about before, and presumably also some kind of a sufficiently convincing argument that your algorithm actually does the job, that it is correct. Okay, so maybe a difficult task, but at least conceptually what you have to do is straightforward. But what if the answer is no? Okay, you think that you cannot implement object A using object B, but you have to demonstrate that to your boss because you're afraid if you say, well, I cannot do this, she will fire you and hire somebody else who can do it. How could you argue that this is not possible? Well, one way of doing it is the following. To show that A cannot be implemented using B, you could show that A can do something that B cannot do, that A can solve some sort of a problem that B cannot solve. So in terms of pictures, here are the two objects A and B. And here is the sum problem P that A can solve, indicated here with a green arrow, but B cannot solve, indicated here with the crossed out red arrow. Well, these two things imply that B cannot implement A, because if B could implement A, then you would be able to use B to solve P by first implementing A and then using A to solve B. Okay? So this is going to be the way in which we can demonstrate that an object cannot implement another. So you see here that P is, or can be thought of as a yardstick that you use in order to compare, to measure the power of A against the power of B, to compare the powers of the two objects to implement one another. And Herlihy's key insight was that the right yardstick for comparing the power of objects to implement one another is this famous consensus problem that you have heard about many times. It allows a set of processes to agree on one of their inputs. Okay, so here comes now the key definition. We're going to attach a number to each object called the consensus number. And this is going to be the maximum number of processes for which this object can solve this problem of consensus. Okay? So consensus number is n. For object A, it means that A can solve consensus for n processes, but it cannot solve consensus for n plus 1 processes. Now, if there is no such maximum, meaning that A can solve consensus for any number of processes, then we say that its consensus number is infinity. Okay, so I attach to every object a positive integer or infinity. And now the consensus hierarchy is simply the hierarchy in which I place each object at the level that is equal to the consensus number of that object. Okay, so level 1 has the objects with consensus number 1 that cannot even solve consensus for 2 processes. Solving consensus for 1 process is trivial, right? I mean, Level 2 has the objects that can solve consensus for up to 2 processes, but not for 3, and so on. So pictorially, it looks like this. At level 1, we have registers. You've seen 2 weeks ago that registers cannot solve consensus for 2 processes, and trivially, they can solve consensus for 1 process, so they're at level 1. There are other objects in this level that you have seen, for example, snapshots. For example, the object of a counter that, that Rachid talked about again a couple of weeks ago. I think 2 lessons ago. That has an operation called increment that allows a process to increment the value in the counter, and a separate operation called read that returns the value of the present value of the counter, and so on. So there are various other objects at level 1. At level 2, we have a variety of familiar objects, such as registers with a test and set operation, or with a fetch and increment operation, or with a fetch and add operation, and other objects like queues, stacks, priority queues. But every level in this hierarchy has something in it. So, for example, level n has something called an n-bounded pickable queue. It's not important if you don't know what that is. Something that I confusingly called n consensus, I think in Rachid's terminology would be consensus n. It is an object that allows n processes to solve consensus. N atomic assignment, it's an object, you can think of it as a shared memory where you can specify n locations and n values, and then in one atomic step assign these values to these n locations. This happens to be in level 2n minus 2. And at level infinity, there are again a whole bunch of familiar objects like consensus or consensus infinity if you want. Compare and swap, register with a compare and swap operation, or a memory-to-memory swap. This is a shared memory in which you can specify 2 locations and then in one atomic step have the contents of these 2 locations swapped, and others. Okay, so this is what the hierarchy looks like. So every object belongs somewhere in this hierarchy, and every level of this hierarchy has something in it. Now, an interesting question to ponder is, why is consensus the right yardstick? In principle, I could have used any problem to hope to separate the power of 2 different objects as the sum problem P. Remember in that picture I had before. So for instance, I could have used the problem, the leader election problem. What's this problem? Basically, informally, it is a problem where a set of processes can agree on one of them to be the leader, one and only one of them to be the leader. Okay, so I could have used this problem and then defined the leader election number of an object to be the maximum number of processes for which the object can solve the leader election problem. And I would get a hierarchy. But it would not be a very interesting hierarchy. It turns out that it would only have 2 levels. It would have level 1, where the level 1 of the consensus hierarchy is, and level 2, which is where all the other objects would be. You can think of this after this lecture if you want. The fundamental reason is that if you can do leader election for 2 processes, you can do leader election for any number of processes. You might want to think about how to do that. It's not true about consensus. If you can do consensus for 2 processes, you cannot do consensus for 3. For up to 2 processes, you cannot do consensus for 3 processes. So the leader election problem is not a very discriminating yardstick to use for comparing problems, in contrast to consensus. So what is special about consensus? What makes consensus a good yardstick? Well, it's exactly what Rachid showed you in the previous hour. It's the universality theorem. Okay? An object that is at level n is universal for up to n processes. You can use it and registers if you need them to implement any object whatsoever that is shared by up to n processes. Okay? And this means that in some sense, objects that are at higher levels of this hierarchy are more powerful than objects that are in lower levels. In what sense is this true? Well, they are universal for more processes. Okay? All right, so now you know what the consensus hierarchy is. And in the next part of the, by the way, before I go on, is there any question about what the hierarchy is and what the consensus number is? Because if this is not understood, then the rest of the lecture is useless. Okay, I think we are. All right, so I'm going to give you an example of how to determine the level of an object in the consensus hierarchy. Okay, and specifically, I will show you that Q is at level 2. I chose that because I think it's an interesting proof, which is contained in the paper I mentioned before, Morris Hurley's paper. So to show that the Q is at level 2 of the consensus hierarchy, I have to show two things. I have to show that using queues and registers, we can solve consensus for 2 processes, but we cannot solve consensus for 3 processes. Now, the first part I will not do because, again, Rachid did it a couple of weeks ago. He showed you how 2 processes can use a queue that was initialized to contain 2 elements called winner and loser to solve consensus between the 2 of them. Okay, if you don't remember, you can go back to that lecture, or you can think about it on your own. For 2, 2 is a bit harder. We're going to use a bivalency argument proof. This is a proof technique that is very useful in this area. It is used a lot. You've already seen an example of such a proof. Again, Rachid used this technique to show you that registers cannot solve consensus for 2 processes. But because it is such a fundamental technique, I thought that it would be nice to show you another instance of this argument in a somewhat more sophisticated setting. So we're going to use it to prove that we cannot solve consensus using 3 processes. Sorry, we cannot solve consensus for 3 processes using queues and registers. So the proof goes by contradiction. We're going to assume that there is an algorithm, let's call it A, that solves consensus for 3 processes. Let's call them P, Q, and R, using queues and registers. And now I will reason somehow about this algorithm, and I will show you that there's always some kind of a contradiction, meaning that this algorithm cannot exist. You can visualize an execution of the algorithm A as this chain of nodes, okay, where every node represents what we call a configuration, that is the global state of the system at some point in time, meaning the states of all the processes and the states of all the objects in the system. Okay? And then the arrow, an arrow between 2 configurations corresponds or represents a step of a process by which the process applies an operation to the object, receives back a response, and changes its state and changes the state of the object. Okay? So, by the way, this chain represents an execution. But if you look at a particular configuration and node there really should be 3 arrows coming of it because there are 3 processes. And any one of these processes could be taken the next step. An execution is just a path through this tree. Okay, so this is what the execution looks like, a chain of configurations where successive configurations, each configuration is obtained from the previous one by a single step of one process. All right. Remind you of some definitions that you have seen before. A zero-valent configuration is one from which it is impossible to reach a configuration in which some process decides 0. Okay? So if you look at all the possible configurations in all the possible executions that start from that configuration, you will never find, the only kind of decision you will find is a 0. So intuitively, what that means is that in this configuration, the fate of the decision has been determined. Okay? If God were to look at this configuration, maybe no process has decided yet. Okay? But if God were to look at this execution, that God would say, okay, well, the only possibility here is 0. There's no way that we can get 1 in any possible future. There is, of course, a corresponding notion of a one-valent configuration. And then configurations that are neither zero-valent nor one-valent are called bivalent. So these are configurations in which the fate of the decision has not yet been determined. There is a possibility that the decision will be 0, and there is also the possibility that the decision will be 1. Okay, claim number 1. Our algorithm A has what I call a critical configuration. What's a critical configuration? It's one that is bivalent, so the decision has not been determined yet. But if any process takes a step, the resulting configuration is univalent. Okay, so the decision has not been determined yet in this configuration, but in the next configuration, no matter who takes the step, the decision will be determined. Why should there be such a configuration? Where? Well, there is an initial configuration that's bivalent. If process P has input 0 and process Q has input 1, that's a bivalent initial configuration. Why? Because if only P takes steps, the only safe thing for it to decide is 0. And if only Q takes steps, the only safe thing for it to decide is 1. So since both 0 and 1 are possible decisions starting from this initial configuration, it is bivalent. All right. If this bivalent configuration is critical, I'm done. If it's not critical, then by definition, there must be a step by some process that leads to a bivalent configuration. If this configuration is critical, I'm done. If not, again, by definition, there is some step of some process that results in a bivalent configuration. And so on. And so on, but this so on cannot go on forever, because if it did go on forever, I would construct an infinite execution in which every configuration is bivalent, meaning nobody ever decides. So at some point, this has got to stop, which means that no matter who takes a step, the resulting configuration is univalent. Well, this is my critical configuration that I promised you exists. Because the critical configuration is bivalent, one of the processes' step leads to a zero-valent configuration, another process's step leads to a one-valent configuration, and the third process's step leads to either a zero-valent or a one-valent. I don't know which. Okay, so we're done with claim 1. There is a critical configuration. Claim 2 is that in this critical configuration, the step that the three processes are about to take accesses the same object. Okay, well, we know that there is some process whose step leads to a zero-valent configuration, let's say process P, and some process whose step leads to a one-valent configuration, let's call it Q. If these two processes access in those steps access different objects, let's say X and Y, different from each other, then it's easy to see that what P does with object X has nothing to do with what Q does with object Y. So the order in which these two steps are executed is totally irrelevant. The picture looks like this. If P goes first and then Q, or Q goes first and then P, we wind up in the same configuration. We say that the two steps commute in the configuration C. And that, of course, is impossible because we can never have a configuration that follows both a zero-valent and a one-valent configuration. Zero-valent means that the only possible decision in any future is 0. One-valent means that the only possible decision in any future is 1. Okay, we have a contradiction. Okay. So what does this tell me? It tells me that X and Y are the same object. They must be the same object. Otherwise, we have this commutativity. All right. Now, what about the third process? Well, let's say that R accesses a different object, Y. I know that R step also leads to a univalent configuration. Could be either zero-valent or one-valent. If it's zero valent, I can play the game that I showed you before with respect to the step that Q takes and get a contradiction. If it's a one valent configuration, you guessed it, I can play the same game with P's step and get a contradiction. So Y must also be the same as X. So all three processes are about to access the same object. Claim 3, this object cannot be a register. I will not show this to you because Rachid showed you essentially this thing in his proof 2 weeks ago. If you don't remember how, go back to that lecture, or better yet, after this lecture, try to reconstruct the proof on your own. Well, since our algorithm only is supposed to use queues and registers, it follows that X must be a queue. So the three processes are about to execute some step, some operation on the same queue X. And we know that we have some process, let's call it P, whose operation takes us to a zero valent configuration, and some process Q, whose step takes us to a one valent configuration. Okay, so now I'm going to do a case analysis depending on what the two operations are. And I will show that in every case there is some kind of a contradiction. Remember, it's a queue, so there are two kinds of operations, enqueues and dequeues. The first case that I will consider is when both processes, remember there is a third process, but these are the two processes that lead to a zero and a one valent configuration. Both of them are dequeuing something, are about to dequeue something from the queue. So both of them will, of course, dequeue whatever happens to be the first element of the queue. Let's call it A, or empty if the queue is empty. And now consider what happens when the other process takes a step. So Q takes a step starting from the top configuration. It will apply, of course, what its next operation is, which is dequeue. And it will dequeue some different element, that's what used to be the second element in the queue, B. And correspondingly, let's make P take the next step from the bottom configuration. It will also dequeue what was the second element in the queue, B. Now compare these two configurations. Okay? The queue is in the same state. It is what it used to be in configuration C with the first two elements removed. All the other objects are in the same state because we haven't touched them. Process R is in the same state because it hasn't taken any steps. So these two configurations differ only in the states of P and Q. Only P and Q can tell the difference between these two configurations. That's bad news because we have a third process, R, that's supposed to be able to tell the difference between these two configurations. So we're going to let this process R take steps all by itself until it decides, starting from the top configuration. Because this follows a zero valent configuration, it will have to decide zero. But because the two configurations that I have circled there differ only in the states of process P and Q, and R, and these processes do not take steps in this execution of R, it's only steps of R, exactly the same steps are applicable starting from the bottom configuration. So R will again decide zero. Well, that's now a contradiction because it decides zero following a one valent configuration. So that's bad news. Well, all it means so far is that the two operations that are about to be applied by processes P and Q cannot both be dequeues. Okay? So now we will consider the next case, which is that the one process is applying a dequeue and the other process is applying an enqueue operation. Here I have to consider two subcases. You will see why. First, I will consider the case where the queue that they both are about to access is not empty. So think about it. We have a queue, not empty, and two processes. One of them is putting something at the end of the queue. It's enqueuing element B, Q. And the other is removing the first element of the queue. Okay? It's not hard to see that these two steps commute at that configuration. Because whether you first add something to the end of the queue and then remove the first element of the queue, or you first remove and then add, you end up with the same queue. And of course, the processes have exactly the same states. In both cases, P has dequeued the same element, and Q has simply enqueued its element. So, we have that. We have already seen that this is a contradictory situation, so this cannot be. What about if the queue was empty? Now the two steps do not commute, okay? Because if the dequeue happens first, it will return empty. If it happens second, it will return B, the element that is being enqueued. So we cannot use the same argument. But what we can do is the following. We will let Q perform its step from the top configuration. You see, P's step that's dequeuing an empty queue does nothing to the queue. Does something to it, but nothing to the queue. So if I now enqueue B, and I compare these two configurations, you will see that they only differ in the state of the process P, which in one case took a step, and the other it has not taken a step. This is bad news, because now I have actually not one, but two processes that could take steps and give me a contradiction. So this time I don't even have to involve the third process. I will let Q take steps until it decides. Starting from the top configuration, it will have to decide 0. Exactly the same execution is applicable to the bottom configuration. It will decide 0 following a one-valent configuration. That's a contradiction. Okay, so the second case, where one is doing a dequeue and the other is doing an enqueue, is also not possible. So finally, we come to the last case, which in some sense is the most interesting one, where both processes are about to enqueue an element to the queue. So one of them is going to enqueue A, the other is going to enqueue B. So let's let the other process take the next step. So as usual in the top configuration, I have P enqueuing A and then Q enqueuing B. And in the bottom execution, I have the opposite. Q is enqueuing B first, and then P is enqueuing A. Let's look at what is happening to the queue after these two steps in these two different executions. If initially the queue contains some sequence of elements, I've indicated them here as alpha. In the top execution, the queue after these two steps contains alpha followed by AB. And in the bottom, it contains alpha followed by BA, because this is the order in which the two elements were enqueued. So let's compare these two configurations. They differ only in the state of the queue. All three processes have the same state, because P and Q have just enqueued their elements. They have gotten back a response saying, OK, you've enqueued your element. It doesn't matter whether they go first or second. They don't know that from an enqueue. Process R has not taken a step. The other objects haven't been touched. But the queue is different, and that's dangerous, okay? Because the processes could dig enough into the queue to see whether the last two elements are in the order AB or in the order BA, and distinguish between these two configurations. So I have to work a little bit now to erase this difference between the two configurations. But I have enough processes to do that. So let's see how to do this. So I'm going to let P take steps by itself, starting from the top configuration, until it dequeues the element A. You might say, well, how do you know that it will dequeue the element A? And I argue that it must dequeue the element A before it decides, because the only way that it can tell the difference between the top configuration and the bottom configuration is by digging enough into the queue to see whether the penultimate element is A or B. Okay, so before it decides, it will have to dequeue A. Now, in the process of this execution, maybe it has accessed other objects, but whatever it has done to the other objects is, and also the queue, and maybe it has enqueued a whole bunch of elements to this queue that I indicate with A prime. So at the end of this execution, the queue contains B, followed by the elements that P may have enqueued alpha prime. Alpha prime could be empty. Now, because the two circled configurations differ only in the state of the queue, exactly the same steps of P are applicable starting from the bottom configuration, except that the very last step will be to dequeue B instead of dequeuing A, because that will be the first element in the queue at that point. Okay? So if you look at these two configurations now, they differ in the state of process P because P can tell the difference. It has dequeued A in the top execution and B in the bottom execution. And the queue is different, but now notice that the queue is a little bit less different. It only differs in the first element. I will need to continue this execution to continue my argument, and I don't have any more room, so I will kind of compress things to the left. It's exactly the same picture as before, except a little bit compressed. And now I will let Q do the dirty job of removing something from the queue and erasing the difference. Okay, so I let Q take steps by itself until it dequeues B, and it will have to dequeue B for the same reason that I explained before for P. In doing so, it may enqueue a few more things into the queue, alpha double prime, perhaps empty. But because the two configurations differ, again, only in the state of the Q and P has not taken any steps here, this execution of Q is applicable to the bottom configuration, except that at the very last step, instead of dequeuing B, it will dequeue A. Now, these two configurations differ also in the state of process Q because it also knows the difference. But now I have erased the difference of the Q in the two configurations. Now all the objects are the same, okay? And process R that has not taken a step is the same in both configurations. So again, I will compress the picture one more time, and I will give the final nail to the proof. R will now take steps by itself until it decides, starting from the top configuration. It will have to decide 0. The same steps are applicable to the bottom configuration because now all the objects are in the same state, and the only two entities that know the difference between the top and bottom configuration, the processes P and Q, are not taking steps anymore. So R will again decide 0, but now it decides 0 after a one-valent configuration, which is a contradiction. All right, after this long argument, we have concluded that all cases lead to contradiction. So our algorithm that we claimed could solve consensus using, for 3 processes using queues and registers cannot exist. So I cannot solve consensus for 3 processes with queues and registers. Okay. So we now get finally to the last part of my presentation. I want to make some comments about what the consensus hierarchy does not tell us about objects. I mentioned in concluding the first part, I think it was in concluding the first part, that there is some sense in which objects that are at higher levels of the hierarchy are more powerful than objects at lower levels in the hierarchy. And that is true. They are universal for more processes. But there are ways of misinterpreting this statement that we should be careful about. So if an object A has consensus number n, we know by the universality theorem that it can implement any object that is shared by n processes. But what about A implementing objects, even weak objects, objects at lower levels in the hierarchy, for more than n processes? Okay, so to give you a concrete example of the kind of question that I mean here is, consider the following. Can the object 3 atomic assignment implement a fetch and increment register shared by 5 processes? Now, 3 atomic assignment has consensus number 4. Never mind what it is. It's not important for my argument. Fetch and increment is at level 2, seemingly weaker. Okay? If I had asked you, can 3 atomic assignment implement fetch and increment for 4 processes or fewer, the answer would have been, of course. Okay? 3 atomic assignment is at level 4, so it can do anything for up to 4 processes. In particular, it can do fetch and increment. Okay? But I'm asking you, can it do fetch and increment for 5 processes? So the question in informal terms is, does the consensus number of an object tell me something about the implementation power of that object for systems of all sizes? Or to be a little bit more precise, or I think quite precise, is it the case that the consensus number of an object A is greater than or equal than the consensus number of an object B if and only if A implements B for systems of any size, for any number of processes? It would be great if this is the case. Okay? Why? Because then this very abstract and unclear concept of, or very, this very abstract concept of what the object can implement would be completely encapsulated by a very simple quantity, its consensus number. And as we have seen in the second part of my presentation, we have at our disposal very nice methods for determining the consensus number of an object. So this would be great, but unfortunately it's not true. Okay? So for every level of the hierarchy, we know that there are objects at that level, so they're at the same level of the hierarchy, such that one cannot implement the other for more than n processes. This has been known for a while for non-deterministic objects. It was discovered fairly recently for deterministic objects. So at this point, we know that there are deterministic objects at every level of the hierarchy such that one cannot implement the other for sufficiently many processes. So let's think a little bit about what is it about the consensus number that is limiting our ability to encapsulate the implementation power of an object just by that one number. And the limitation is that the consensus number tells us something, actually tells us a whole lot about what the object can do for systems of up to a certain size. It doesn't tell us very much about what that object can do for what size, the size that is equal to its or below its consensus number. It does not tell us very much about what the object can do for larger systems. We know that there are some things that it cannot implement. If it could implement things at higher levels, then it itself would be at a higher level because it could solve consensus for more processes. But it doesn't tell us about what it can do about whether it can implement other objects for more processes. So how can we perhaps hope to overcome this limitation, that it doesn't tell us anything about what happens for larger systems? Well, there comes the problem that Rachid called consensus N, I think, and which I will be calling K set agreement problem. I will not use consensus for this problem to avoid confusion. So the K set agreement problem is a generalization of the consensus problem this generalization. You don't have to read the details. Essentially, it says that I want a set of n processes to agree not necessarily on one value, but on at most k different values. K of different values that are their inputs. Okay? So one set agreement is exactly the same thing as consensus. K is equal to 1 means we will all agree on at most one value. Okay, that's consensus. Two-set agreement means that, well, some processes may decide on one value, and a different set of processes may decide on a different value. Three-set agreement means that there could be three different sets of processes, each deciding on a different value, and so on. So you can see that the bigger the k, the easier the problem. Rachid mentioned that already. Until the k is equal to n, in which case the problem becomes trivial. Everybody can output their own input. But even for k is equal to n minus 1, the problem is non-trivial and interesting. And now, so this is the generalization of k-set agreement, and you will see how this will allow us to overcome this limitation of the number of processes for which we know something. I now have a generalization of the notion of consensus number. I will define the set agreement power of an object to be an infinite vector of positive integers, the kth of which is the maximum number of processes for which the object can solve k-set agreement. Okay? So n1, the maximum number of processes for which the object can solve one set agreement. That's the consensus number of the object. The first element of this infinite vector is the consensus number. The second element is the number of processes for which the object can solve two-set agreement. Okay? That number is bigger than n1. It's at least twice n1. N3 is the number of processes for which the object can solve three-set agreement. Okay? So I get this infinite vector of increasing integers, so I have now something that tells me about what the object can do for an arbitrarily large number of processes. And now I can ask a question very similar to the one that I had asked before. Does this object, this infinite vector, encapsulate precisely the ability of an object to implement other objects in systems of all sizes? I have some hope for this now, because I know something about what this object can do for systems of arbitrary size. So again, to make this more formal, I could say, is the set agreement power of object A greater than or equal than the set agreement power of object B, if and only if A implements B for any number of processes? Now, I have to tell you what I mean by greater than or equal to now, because these are vectors, infinite vectors, not integers. Well, I mean component-wise comparison. I mean that the kth component of the first vector is greater than or equal than the kth component of the second vector. Okay, so I came across this idea in a paper that has deep French roots. It was co-authored by Carole Delporte, Hugues Fauconnier, Eli Gaffney, and Petr Kuznetsov. Not quite in this formulation, but I think the underlying idea is captured by this formulation, and they were interested specifically in deterministic objects. Now, this would be great, again, for a similar reason. If this is true, then this amorphous notion of implementation power of an object would be captured by a very nice mathematical object, this infinite vector. Now, that's not quite as simple as the consensus number, and we don't have as nice tools for figuring out what the set agreement power of an object is. But nevertheless, mathematically, it would be very nice if this is the case. But unfortunately, this is not the case either. We we now know that for every level of the consensus hierarchy, from level 2 on, there are objects at that level that have actually the same set agreement power. So they don't agree just on the first component, they agree on all the components of the set agreement power, but one cannot implement the other. Okay, this was proved for non-deterministic objects last year and for deterministic ones this year. Unlike the previous result that I told you about, similar result for the consensus number, we don't know what happens at level 1. We don't know if this is true or false at level 1 of the hierarchy. And let me conclude with a few comments about another property that we wish or wished the consensus hierarchy to have. Suppose so this is another, so this property is called robustness. Suppose that I give you two objects, A and B. They have consensus numbers m and n. We know that A by itself is universal for m processes. B by itself is universal for n processes. Another question is, suppose I give you both of them at the same time. I give you an object that's the combination of A and B. Okay? For how many processes is this combination universal? Clearly, it is for at least the maximum of m and n. Okay? Because with the two objects, you can do at least as much as you can do with the better of the two. Now, maybe it is more than the maximum of m and n. So the consensus hierarchy is robust if basically this is not the case. It is not greater than, it is equal to the maximum of the two. So more generally, the consensus hierarchy is robust if the consensus number of a set of objects is the maximum of the consensus numbers of the individual objects. This would be nice because then it would tell me that if you give me a collection of objects, basically I can throw out all of them except the most powerful one, and that would be just as good. Well, unfortunately, this is not true either. Okay, there's been a succession of papers, the last of which, not particularly new ones, the last of which showed that at least if our world of objects includes non-deterministic objects, the consensus hierarchy is not robust. We can take objects that are individually weak, in fact they're at level 1, and construct objects that are arbitrarily high in the hierarchy. The combination of the two objects is arbitrarily high in the hierarchy. Now for deterministic objects, it is not clear to me at least what the answer is to this question. There have been two papers from even longer ago, from 1994, that claim that the consensus hierarchy is robust for deterministic objects, but I do not understand the arguments in this paper, so at least in my mind, this question is still open. Interestingly, if we restrict our attention to objects for which the set agreement power conjecture is true, that is, objects whose implementation power is fully encapsulated by the set agreement power. It's not all objects, because we know that the set agreement power conjecture is not true. But if we restrict our attention to those objects, it turns out that the consensus hierarchy is robust for those objects. Okay, we have come to the end of my presentation. Thank you very much for your attention. I have here 2 pages with the papers that I have used in my presentation. This is the first page. This is the second page. I will be happy to answer questions or hear your comments.